Hello and welcome to episode 86 of the HamCorp Training Manual. In this episode, we craft the first ZPM energy hatch, allowing us to finish the supercritical steam turbines for the solar tower setup. Also, we finish working on the water line for now by setting up grade 4 pH neutralized water. Between episodes, I redid the monazite line, and my goal was to make it easier to understand what's going on here, and I think I have failed to do that. And to be honest, at this point, I'm pretty convinced it's not possible to make the monazite line look nice and look sensible, because it's just so, I don't know how to put it. It's just so convoluted and long. I don't know. I don't think it's possible. I did change the layout for my GregTech cables and my Applied Energistics cables as well. At least those make sense to me. Like, it's easy to follow things around. And if I want to overclock this whole setup, all I have to do is swap out the energy hatches, swap out the cables. That's it. Now, more importantly, we have grade 3 water from the last episode, and I can use this to make ZPM energy hatches. The next step is to make europium doped wafers, and these are supposed to be more efficient than using Naquata, so I will be probably swapping over to this as much as I can. It uses a lot of poly-Si solar grade silicon, but that's to be expected at this point. But it also cuts into a stack and a half of wafers. And these wafers, of course, give you even more engraved wafers when you put them in a laser engraver compared to the previous tiers. In the last episode, I also figured out an EU equivalent for 1 liter of each of these grades of water. I can use those numbers to go through my laser engraver recipes and my cutting recipes to see where it actually makes sense to use these filtered waters. Because it doesn't always make sense. Sometimes distilled water is a little bit slower or whatever, but it doesn't use an insane amount of EU. Maybe I'll get to the point where EU is no longer the issue and it is indeed processing time, and at that point I'll switch, but for now I'm only going to switch quite sparingly. But alright, let's keep going. Europium doped wafers. Next up, the nanopower ICs. This is a ZPM cutting machine, so I'm gonna have to upgrade. Now, to make the ZPM energy hatch, it's not that bad. I've made most of these things before, except for the ZPM voltage coils, which are not bad because it's just europium and samarium. There's a choice of different coolant cells, and I think I'm going to use the space coolant cells because they're made of Callisto ice and Ledox dust, which I don't really have a use for, not a significant use, so I figured this is a good place to use these. And then besides that, you know, circuit components, pump, coolant, same shit as usual. I do have to scan an LUV energy hatch, and it's a pretty long scan. Once this is done, I'm going to make a couple ZPM energy hatches and just go around the base to all the places where I've doubled up on LUV hatches and just upgrade them to ZPM. Because I just don't like doubling up hatches. While the LUV energy hatch scans, I've just been looking through the quest book a little bit, and after doing the ZPM energy hatch, I think I'm going to go back to my solar tower setup and finally set up the extra large supercritical steam turbines. And after that, it's time for more fusion, I guess, but I could also do grade 4 water. And that seems kind of fun. And while the water line is still fresh in my head, I think it would be good to do this. So I think I'll do this first and then fusion. Also, I have no idea what these 4 quests are about, so I'm just going to mark them as done. Okay, I am in the process of upgrading my energy hatches, and I'm just going to do a double energy hatch setup for now. I don't want it to be permanent just yet, just so I can smelt my dalasonite for my extra large supercritical steam turbines. Hopefully a high amp transformer with a Tesla cover should be able to cover this. We'll see. I'm using Naquata cables for ZPM, just because they're the easiest ones for me to make right now. Supercritical steam turbines are now in place. Everything is running fairly smoothly. I have had some issues with these solar towers. It's really hard to get a system working that you can just set up and forget. So let me guide you through this whole process. Also, I made these cool looking screens. You like those? So let's start at the solar towers. All 3 of them are set up in exactly the same way. I have my output hatch going into ME. I have an input hatch, which is a ULV input hatch, and that is important. It needs to be a ULV input hatch because you want to limit the amount of solar salt that can go in to 8,000. You don't want to supply more than that. That solar salt comes from this fluid tank. Fluid tank has a machine controller cover on with a redstone signal leading to it, and I'll come back to this redstone signal. And it also has an electric pump with the condition set to use machine processing state. So when there's a redstone signal, the pump will activate. The redstone signal is basically only ever on when we want the turbines to be running, because the solar towers are always running. But at night, they don't generate heat. So we don't want to supply the coolant at night. Here I have a fluid P2P tunnel. These are the output sides. And these come from the extreme heat exchanger. So the output of the extreme heat exchanger is cold solar salt. That goes into this fluid P2P tunnel, and then it's split between the 3 solar towers evenly. That's the nice thing about using P2P tunnels here, is it splits the flow evenly between all of the output locations. I have 24,000 solar salt in circulation, so that's 8,000 for each of these. And the extreme heat exchanger now has a fluid storage bus on the input for hot solar salt, and that makes it so we generate supercritical steam. That is in this output hatch with a fluid storage cell, because it makes a lot. And this goes to the turbines. These are stored in super tanks at the 2 turbines, and these super tanks have a fluid regulator. One of them is set to 76,800, which is the optimal flow rate, and the other is set to the remainder of what I make. You don't want to make it 76,800 here as well, because then you'll have kind of an annoying situation where this keeps turning off and on, and that's kind of happening now, and I'm not sure why. I'll have to investigate a little bit more. But anyway, on top there is a fluid detector cover, so that whenever there is a fluid inside of this super tank, we turn on the turbine. There is a startup time to the turbine, so that's something to be aware of. And this will produce quite a bit of power. This will make superheated steam, which goes in here, which makes regular steam, which goes in here. And besides that, it's exactly the same setup on these 2 columns, except one is at the optimal flow rate and one is at less, because I don't make enough to have 2 optimal flow rates. I've tested this for a few hours and it's been mostly stable. I have had a small issue though. When it starts raining, it seems like the heat gain on the solar towers decreases. And I never noticed that before because I wasn't using 8,000 solar salt. I was only using, I think, 7,000. That small difference managed to make up for it. But I think now that it rains, we're going to have to do a little bit of additional logic. This I haven't extensively tested, so this might be a little problematic. But let me show you the redstone circuit anyway. Before, I had a timer, and I just turned on the timer manually at dawn or dusk, and then just had it set to 10 minutes so that it would turn everything off at dawn or dusk and on again. That's a little annoying because I can't sleep to skip the nights. Not that I really need to anymore, but it's very easy for that timer to get desynced from the day-night cycle. So instead, I have here a daylight sensor. This emits a redstone signal whose strength depends on the time of day. And here I have another signal coming from a lever. That's just, the point is I wanted it to have a signal strength of 4. I've also tried it out with the signal strength of 3, and that seems to work pretty well as well. There's a lot of testing going on, to be honest. It's not really a finalized design. Also, if there is a better way to just generate a 4 strength signal than doing this, please let me know, because this is really ugly. Both of those signals lead to this comparator on the subtraction side. So the signal you get out is the daylight signal minus 4. And that makes it so that everything turns on at approximately the right time. It's really hard to get it to be precise without like open computers or something. Anyway, for rain, here's a rain sensor. This basically just outputs a signal when it's raining. And if you put a signal on this side of the comparator, it kind of acts like an override, and it just turns it off. So I have a lever here to demonstrate, like so, and this would turn off. All right, now as you can see, it's nighttime, and the signal strength here is 4, the signal strength here is 4, so the signal strength here is 0, and everything should be off, and hopefully all the heat levels are above 50,000, and they are. So that's a good sign. Dealing with the day-night cycle is the hardest part of this. If you're in the personal dimension and you set this up, you don't even need to think about it. You just permanently have everything going, and it'll work perfectly fine. But cool, I have been running this for quite a while now, and I have almost a full output hatch of grade 3 water. Oh, one final note about the Lapatronic supercapacitor here. It needs to have a big enough buffer to last through the night. So with a bit of testing, I found that having 9 IV supercapacitor cells manages to make it through the night. So cool, that's done. pH neutralization. In case you don't know, pH is a measure of how acidic or basic a substance is, in this case the water. So if the pH is lower than 7, it's acidic, and if you add a base, it will neutralize it and bring it to 7. If it's greater than 7, then it's basic, and you need to add an acid to neutralize it. That's basically how this works. So I have my input and output on the back. As you can see, I've tested it a few times, and this does seem to work pretty consistently. On the structure, I have 2 pH sensor hatches. The one on the left is set to 6.96 and is inverted. So when the pH of the input is less than 6.96, then we get a redstone signal. And on the right, we have the opposite. So 7.04 and set to normal. So when the pH is greater than 7.04, we get a signal. The initial pH is randomly determined. It's just some number between 4.5 and 9.5. And every 20 ticks, so 1 second, the purification unit looks at how much sodium hydroxide is inside the input bus, and it looks at how much hydrochloric acid is inside the input hatch over here. It consumes everything in the bus and everything in the hatch and calculates a new pH. Every piece of sodium hydroxide dust will bring the pH up by 0.01. And every 10 liters of hydrochloric acid brings the pH down by 0.01. If the final pH value at the end of the cycle is within 0.05 of 7, so between 6.95 and 7.05, then the recipe succeeds. Otherwise, it 100% of the time will fail. So what we need to do is, if the pH is too low, we supply some sodium hydroxide. If the pH is too high, we supply some hydrochloric acid. And that's what these signals are for. So on this side, on the input bus, it's a ULV input bus, so that there's only one stack of sodium hydroxide going in at a time. There's a machine controller cover on the left, and there's an input bus set to import and use machine processing state on the top. Importantly, this is an MV conveyor module. We don't want to pull in the sodium hydroxide too fast. So every time a stack is consumed, the pH goes up by 0.64. On this side, we have something similar. We have the machine controller cover. And on the top, we have an LV fluid regulator set to -5 per tick, and conditional is on. So this is negative because it's on the hatch, not on the tank, so it's importing. So every 20 ticks, the pH will go down by 0.1. So it goes up by 0.64 or down by 0.1 at the end of every cycle. When the pH is within the acceptable range, there is no redstone signal, so nothing will be provided in the inputs and outputs. And eventually this will stabilize. The most important thing is just that on each cycle completion, you don't want the pH increase amount to ever be equal to the pH decrease amount. Because if this went up by 0.64 and then this went down by 0.64, you're just going to oscillate above or below the accepted range. So they do have to be different, and they will eventually stabilize. But the question is, can it stabilize within the 2-minute window? Because you have 120 cycles to get this done. That's honestly more than enough. So let's start a cycle. And here it is, it's working. So if I scan this, the pH is 6.33 right now. 6.97. It's gonna go up one more time. Oh wait, no it's not. 6.97 is within the accepted range. So there you go. If it was lower than 6.94, it would go up again, and then the hydrochloric acid would bring it down. This stabilized pretty quickly. But I think that was a little lucky. But I'm just going to let this run now, and if I do run into issues, if I notice, I'll let you know. Thank you for watching this episode of the HamCorp Training Manual. In the next episode, we will upgrade our Tesla tower to be able to handle ZPM and hope that the entire base doesn't explode. After that, we will obtain the Tier 4 rocket schematic and build the Tier 4 rocket. See you next time.